me start this. You should be able to see the slides, I believe.
Yes.
Okay, perfect. Well, hello everybody. I'm Asier Arruti from the Mondragon University, and here we have prepared some slides. I mean, the slides go a little bit in detail, but we're just going to go quick above with the main critical points. We're going to start working out the model, our strategy, our main objective when we develop the model. Then we will explain the model itself. And then I added some points to see how we try to fit the model in this evaluation criteria, these important things, right? So first of all, what was our strategy? Well, in the last sentence of the MagNet Challenge Initial Handbook, I believe it was, it says that ultimately the winning method can become a standard way of training data-driven models. And this standard part was like, okay, we have to do something that's generalizable and standard. This was like our main objective, right?
Yeah.
We also wanted to keep it simple, tie it to what's used nowadays, which is mostly the improved generalized estimates equation. And this will also facilitate the adoption of this model, which will help in instance the model. And we also thought that in the MagNet Challenge, we have detailed flux waveforms, but the signals a lot of times have like simplified waveforms, so they don't have very accurate and all the noise and exact form of the waveform. So think about it how when we implement the model, right? Those were our three main objectives. Now that we have the main objectives set, we are going to talk about the model. Now, the model takes the combination of 5 key literature works. The true estimates equation, which was the estimates equation proposed over 100 years ago, which has the separated hysteresis loss and eddy losses. The estimates equation, the model version we typically use, which has the alpha, beta, and k parameters. Then the improved generalized estimates equation that uses flux derivative and peak-to-peak flux density for triangular and trapezoidal waveforms. The composite waveform hypothesis that assumes that you can calculate the segments, the losses of each segment separately and then add together. And lastly, the improved generalized estimates equation, which is an improvement on the generalized estimates equation that adds relaxation losses, right? Now, we have to say that before the MagNet Challenge, this last model, we were working in a model, we call it the composite improved generalized estimates equation that we published just at the end of this year. So we can see that this model is like a fine-tuning and improvement on this model. If you want any detail, you can check it out. But yeah, basically, the model has a pre-processing stage. Instead of using BH, all of the data, we just generate segments. For trapezoidal, it will be 4 segments. For triangular, it was just 2 segments. For sinusoidal, we just take the basic definition of the sinusoidal equation, let's say. And then we combine all the theoretical models to get an equation that can combine all of these critical parts that define the losses, right? And we just take all of the data with triangular and trapezoidal waveforms, except the data with duty 1 equal to duty 3, which is, I think in the MagNet, it's the only case where we have relaxation losses in theory. And then we just get the ideal parameters that define the low frequency losses and the high frequency losses, which are the hysteresis and eddy losses theoretically. Then we have a second stage to estimate the relaxation losses. We see the difference between our estimation and the real losses. So we define a new equation for relaxation and add them. And then we do a new step of refitting the model. So the first 2 stages, let's say that they go to local optimum. This last step ensures that we try to find a global optimum for the model, right? And since the model is just mathematically, we just repeat it for any temperature and any material we want. We just run the model again with new data, and it just gets the parameters. Now, what is our school of thought in this model? Well, accuracy is critically important, of course, but we didn't just aim at optimizing accuracy because you said in the first day that different cores have different losses, discrepancies. They are typically, I mean, in our experience from what we have seen is typically 5%, but sometimes they can go to up 10%. So let's say that there's like a diminishing return in accuracy, right? I guess that if you go below 5%, maybe it's not that important because in practice, you probably have a little discrepancy. So we thought that, okay, if model size and accuracy both have the same importance, let's try to make a good enough accuracy, right? Let's try to make a compact model, easy to use, and just make it good enough. And instead of optimizing for the 95 percentile, we use root mean square because we found that this should be more generalizable, right? You take all of the waveforms. Sometimes it's worse, but in theory, it should be more generalizable. You ensure that you're trying to optimize for all of the data you have. These are the results we obtained. We presented. These are different from the ones we reported because we saw that there's a small error in the code in the waveform classification. They are not that different in most cases, but it's small differences. But the interesting part is if we compare this with the validation data with the fitting data. It's very interesting because it's almost the same. The root mean square and the percentile is very similar. So we can somehow say that we have like a trustworthy model. I mean, that's subjective, but that's interesting also that the 95 percentile, it's basically twice of the root mean square, which is always true for all materials, which is quite interesting. And we have to say that the maximum sometimes is quite high, sometimes quite low, but we should not go crazy with this because it's probably, we have to simplify the waveform. We have a waveform classification algorithm, and we have seen that sometimes it fails. So it's probably the reason why this is happening. But anyways, we still report it here. And from here, you can see all of the materials. And there's one interesting, which is material D, which I think we are not the only ones having problem with that material. And we will talk later what we think happened with this material, right? Mm. Now, model size is another important thing. In theory, it should be as important as accuracy. Of course, I think you talked about the first day in the introduction about this. Like modern hardware, model size, it's becoming less and less important because, I mean, of course, there's a limit, but having a big model is typically not that much of a problem. Of course, there's the subjective part of big, but having a small model, if it's small enough, if it reaches a critical size, you could potentially just put it in a datasheet. So that's actually very interesting. So that's what we try to do. It's a physical analytical based model, right? So we define 3 parameters for a low frequency, which is hysteresis loss, 3 parameters for eddy loss, and 3 extra parameters for realization losses. This we'll explain a little bit later. Now, this is only for now. We have presented triangular and trapezoidal. Sinusoidal data, our model was not prepared for that. We just decided, okay, if data sinusoidal, just fit it to a basic polynomial. It's the polynomial equation. It's just good enough for us. So that's okay. But in theory, it has been demonstrated that triangular and sinusoidal data should be defined with the same parameters, with the same parameters, right? So in theory, we should be able to remove these parameters. We didn't take temperature. If we didn't define these parameters as a function of temperature, we just fit the parameters for different temperatures differently, which it's not optimal, but it just works. It's simple. And we use the same models, same parameters for everything. Well, of course, different, but it's the same model. So we get 9 parameters for the triangular and trapezoidal, plus 6 parameters for sinusoidal, times 4 temperatures. That's 60 parameters per material, which is quite low. Now, did we achieve that critical size? This is the N87 datasheet, and I think that actually yes, because this is just an illustration, but in theory, if you have these parameters and they are quite small, that you could potentially define them in the datasheet. So because the model is very small, you can just put the equation, you don't need anything more. And in fact, the model is so small that you can actually even execute it in Excel, which in academia, yeah, we typically don't use Excel for these things, but in industry, there are still people that are designing push-pull converters with Excel. So that's actually quite an interesting point, right? Now, explainability, since the model is based in physical phenomena, should be very easy to understand the model with, if you know the literature, of course. It should be immune to extrapolation, theoretically, because we use 2 planes for low frequency and high frequency. Because we are basing the improved generalized equation, we also can extract the alpha and beta parameters. Here you can see that hysteresis losses alpha is an average close to 1, which theoretically statements say that alpha should be 1. In eddy losses, alpha is close to 2, and beta is close to 0, which also was a statement said like over 100 years ago. And realization losses are between 0 and 1. Theoretically, from the publication of realization losses, we know that it should be here. Our equation is not equal to them, so we cannot just connect it, but it follows the same logic, right? That's quite interesting. And now, what happened to material D? Not that we have explainability, right? We see that, I mean, it was a problem for us. We see that it was a problem for a lot of other teams. So we check what's really happening. We see the parameters, and we can clearly see that, okay, the parameters for realization are 0 at 25 degrees. These last ones, the last 3 columns, right? Okay, maybe there's no realization data. In fact, there was no realization data, trapezoidal waveform realization. So can we fix this? Okay, let's check the easiest fix we can figure out. Let's copy paste the 50 degrees realization parameters into 25 degree case, and let's test it again. Now we have a new parameters. This is before we check the parameters. It's different from the one we reported, but you can see that it's very high. It's just because the small typo in the code, but it's practically very similar. And this is when we just copy paste the parameters. And you can see it follows the tendency we shown before. They are very similar, the fitting dataset and evaluation, and we get quite an improvement, right? I mean, the maximum is clearly much better under root mean square. So that's actually really good. Now, for the novelty, of course, we are using combination of well-known classical approaches, but we are using this in, let's say, an interesting way to combine this. For example, we are using the extreme duty cycles of triangular trapezoidal waveforms to characterize the composite waveform hypothesis, which gives you much more information without having to make tests at 1 hertz and 10 megahertz. It's quite an interesting approach. We have proposed an alternative way to characterize the realization losses. It should be less accurate than the one proposed before, but for us, for accurate enough approach, I think it's good enough. And we have also demonstrated that just using the 2 planes, hysteresis and eddy losses, that estimates propose over 100 euros, we actually can quite get very good results in a very wide range of flux and frequency. We have shown that you can actually push the estimates-based models quite a lot far away. You can improve the precision a lot while retaining the connection with the classical estimates parameters. So in theory, you can use this approach in the typical designs approaches that use estimates parameters. And even more, you can even integrate other worlds based on the estimates parameters, like the premediation for the DC bias. It's really interesting to see if it actually works or not. And lastly, because we're seeing simplified waveforms, the model should be ready for designers to use this in their typical design workflows, right? Because you typically don't have the measured detailed BH loop or B waveform. You typically have like some coordinates of the points, let's say, and that's all you need to implement the model. So that's really, really interesting. And the code, it's very easy to use. It's super quick. This is N87 model executing everything, characterization, loading data, evaluating data. It takes 10 seconds, and 66% of that is just loading the CSV file. So that's quite interesting. And we have shown that it's super easy to implement. You can even implement it in Excel if you want. So that's great. What has not worked? Well, the data classification we used was not the best. We thought that it was good enough in the first 10 materials. Then the last materials arrived, and we saw that it wasn't that good, but we didn't have time to start changing everything. You have to check all the wafers one by one, and it's too much effort, right? I mean, if we had time, it was better to invest time, but we definitely have to improve this, right? Then what happened with the TLD? We actually should check. I mean, we have the capacity to make informed guesses, right? Because it's a physical parameters, and you actually can improve even if you don't have the parameters to fit the data. You can at least make some conservative predictions. So that's really interesting. We have a big potential to reduce the model size because the improved general equation relates the triangular and sinusoidal data, which we didn't do in this work, but in theory, it is already done. We just have to implement it in our work. And that will be reducing the size from 60 to 36. That's 40% reduction. And lastly, you could, in theory, because this is a physical model, test other things like influence of core size, premagnetization, temperature dependency, extreme extrapolation in ultra-low frequency and ultra-high using the dual plane approach. So that's actually really, really interesting. That's the results we got from here. And lastly, before finishing, I would like to take the opportunity to thank everyone behind the MagNet project. I mean, your objective was to improve or go beyond the estimates equation, and I for sure think that you guys have achieved this. And also, especially because this open source database is critical for the push of science forward. And I really hope that you inspire other groups to do the same. Especially personally, I would like to thank you because I started using the MagNet database before even you started the MagNet challenge. I think back then you had like 5 materials and not this bias. It was in like coming soon, this bias. So I remember that time, and it has been an invaluable sandbox to play during my PhD, and it has definitely saved my PhD. So thank you very much for that.
Yeah, thank you, Ashir. When are you going to graduate? I know it's a tough question. But anyway, thanks for all you presented. Very nice presentation. We only see 2 teams trying analytical model, your team and the next team, which is coming next. And it's very good because this has been 100 years. And it's good to see all the literature tied together. And professors like Professor Charlie Sullivan has been working on this all his career, and he likes to see these kind of methods continuing. And also, it's a science question, right? So if you are asking for 10% accuracy, you guys prove that 60%, 60 parameters can reach 15%, right? So my question will be, where's the limit? That's like a science type question. We know 3 is not enough because 3 statement equation usually give you 50%, 100%, which is not useful in practical design. So it's always a good question to see how can you. I'll be very excited to see the next papers or future publication from your group trying to push it down to 30, and then maybe 20, and maybe 10 and 15. So that's really like mathematical questions. The math community likes this kind of challenge. So my question is, you mentioned your model is very fast and simple. That's for inference. But how about training? How much of your parameter tuning training process is automated? And how was that? If I have a new material, how long does it take for you to get a new model ready?
Let's show you. This is N87. I think it's the material with most data points, I believe, with C94 and 90. We execute it. It's loading, 7-second loading the CSV files. So the first talk it's going to do is just loading the data files. And now it's just classifying data. And it's ready.
Oh,
it's ultra quick because it's
training, including training. Does this including the parameter feeding? Okay.
The graph I sent you here.
Yeah, go ahead.
This one, yes, evaluating the model is like 45 milliseconds. You can see here the time what takes long. The modeling of the sinusoidal data, because it's like a polynomial plane, it's like super quick. But the fitting, it's only 3 seconds for the biggest material. For a material like the last materials you have, it's like 2 seconds. It's very, very.
So you need a powerful, like one of the team mentioned, the memory challenge. So you need to read all of the data into your memory. This means like relatively big memory, but that's fine. It's getting cheaper and cheaper. More and more teams can afford it.
Actually, it's not that big because you read the data, but then you just, I have this set here. When you read the data, you just need these values here, right? It's all you need to execute the equation. So you define, instead of having 1024 points, you just did, if a trapezoidal you have 4 segments, so just the duty cycle of each segment, just the flux change of each segment, just the parameters you will.
Okay, I see. Okay, so that means your waveform classifications that like you said, that part is very important so that you can simplify.
That's why our error goes to quite crazy sometimes. Yeah, that's exactly the point.
Understand. So I would encourage you. I can imagine a online tool that people just throw a database to you with a new material and then you give them a model. That could be very, very useful.
Yeah, definitely. I think that just giving these parameters, knowing that the model is good enough, let's say good enough, it will help a lot in design, right? And it's just interchangeable with IGSA, right? You don't need anything more. You typically use this parameter for IGSA anyway, so it's really interesting.
Yeah, great. Any questions from the audience? Any thoughts on the equation-based approach? Shukai, Hara, any question?
Not really. Looks really good. Like as you said, there's very little. There are very few teams that are really using the analytical model, and this one is quite impressive in my opinion, I think.
Great. Well, what do you think is the limitation? I'll throw a question. Like, what you have 3 waveforms, but now if I gave you a crazy waveform, like that's a trade-off between like neural network approach where it's agnostic, it will always work for any waveform. But now I tell you, you can't get a duty ratio at all, or because it's just like crazy. What do you do with it?
I mean, for example, in theory, and of course we have tests with trapezoid triangular waveforms. In theory, because it's basically in classical approaches, it should be quite extrapolatable to other waveforms. Of course, that's saying a lot. We haven't tested, but I think that you can get good enough accuracy. I don't think you can go much farther than this. I mean, I would love to someone prove me wrong. I mean, that would be ideal, but 10% accuracy will be actually quite good. I think, of course, you always have problems with. Depends also a lot in your waveform classification, right? I mean, I divided my trapezoid in 4 segments, but in theory, in the IGSA, you could actually, a triangular waveform going up doesn't have the same slope flux in the beginning.
Yeah, IGSA is fine. IGSA is agnostic. It's generally applicable.
So in theory, you can try to apply that and check that. I mean, it's very interesting. And the good thing about this is that, Stamets did his original work with iron cores. It's not a ferrite, it's iron, and he showed the same equations basically. So I mean, it appears to be maybe you can extrapolate this to even iron cores and not just ferrite cores. So that's actually very interesting. But I think that if you want to improve the accuracy, of course, as I have said, there's like a diminishing return in going extreme crazy accuracy because it's very good for this core, but what about this core? I mean, there's still a lot to investigate about how much error is average in a core. But I think if you combine this with neural network, you can actually go even a small neural network just supporting this could achieve really crazy accuracies in that regard, right?
That's good. Yeah, that's right. So my intuition is that for typical power converter design, you don't have that crazy waveform. It's usually fairly simple. So this method is good enough. And if you have some additional neural network booster for processing the corner cases, then we're good. So yeah, a lot of remaining challenges and opportunities to address. Great. So we'll move on to next team, Southeastern University, another analytical model.